When you're traveling and don't have a laptop but still need to write, you're stuck typing on your phone or iPad. Typing on those devices is inconvenient, and carrying a physical keyboard is even more inconvenient and bad for the environment. We built a virtual keyboard that uses a phone or tablet camera to detect finger movements on a flat surface and translate them into keystrokes. You still need a stand for the iPad or phone, but you can use it for other things, and it's not e-waste.
This block diagram shows how everything in our system fits together, from the camera to the final typed text. We start from the left with the mobile device camera, which sends video frames into the media pipe hands model. That model gives us hand landmarks every frame. From there, the landmarks feed into three main processing blocks: calibration, which figures out the keyboard's position and orientation; fingertip detection, which estimates each fingertip's contact point on the surface; and tap detection, which decides when a tap happens. In the hybrid mode, tap detection also listens to pressure sensor data coming over serial from Arduino. All of that information comes together in key mapping, which combines the fingertip positions, the keyboard layout, and tap events to decide which keys are pressed. Those key events go to our text editor with autocorrection, and the result is the typed paragraphs you see in the right. The next piece is calibration and mapping to the keyboard. The system uses the two index fingers' position to set the position, rotation, and size of a virtual keyboard layout drawn over the camera view. We will show a demo of the system in later parts of our video. To get those fingertip positions, we use a dedicated fingertip detection stage. Every frame, the media pipe hand landmark model estimates 21st key points per hand. From those landmarks, we first pull out the fingertip joints and then refine them into actual contact points with the surface. We extend a projection line from the pip joint to the tip landmark and look for a large change in color or brightness along the line, which often correspond to the boundary where the finger meets the table. If we find the strong contrast, we treat that as the contact point, and if not, we fall back using a fixed proportion of the pip-to-tip length around that direction. This gives us a reasonably stable estimate frame by frame of where each finger is on the keyboard. Once we have fingertip positions, we first try to detect taps purely with computer vision. For each finger, we watch its motion over time and run a small state machine that looks for a tap-shaped trajectory, lifting up and then a fast downward motion towards the keyboard plane, and then a brief dwell near the surface. We computed a tap score from the vertical speed, distance, and timing to try to filter out media pipe noise and distinguish taps from normal hand motion. In practice, this CV-only hand detection wasn't reliable enough. In our tests, it often ignored valid taps, and even with careful thresholding, it still fired on glitches and random movements. That result made us realize that it wasn't ideal to ask vision to handle both where's the finger and did it really tap at the same time. So we introduced an alternative hardware-assisted tap detection method. In the revised design, vision still provides fingertip location, but hardware decides when a tap happens. We attach thin-film pressure sensors to the fingertip and wire them to an Arduino using voltage divider circuits. When a finger actually presses down on the surface, the corresponding sensor sees a spike, and the Arduino captures the spike to send a tap event. The tap events include which finger it is and when it happens. At that moment, the website looks up to which key polygon that fingertip was inside and outputs the tap event to the text editor. In our testing, the sensor-based method significantly reduced undetected valid taps compared to vision-only version. Our final system therefore supports two modes: a pure vision mode that works with just the camera, and the hybrid hardware-assisted mode that keeps the same fingertip mapping but uses pressure sensors to detect tap timing for much more reliable typing.
Now I'll introduce the website interface. Here we can select between user mode and testing mode from the drop-down window. User mode is the simplified user interface. Under this mode, all developer-only controls are hidden so that the user only sees the essential buttons. On the top left is the Start Front Camera button. When you click this, the app opens the front camera and begins fingertip tracking. The Stop button will turn off the camera stream and clear the overlays. Then we have the Camera Selector, where you can switch between any available cameras on the device. To the right, we have the Connect Pressure Left and Connect Pressure Right. When you click this, a drop-down window will show and ask you to select an Arduino port to connect. This lets the user connect the left-hand and right-hand sensors if they choose to use pressure-based typing. If no sensors are connected, the system will just stay in camera tap mode. The next one is Tap Input, the drop-down that switches between two typing modes. Vision Tap allows you to type without any external hardware. Pressure Taps requires pressure sensors, but provides higher accuracy. By default, it stays on Vision Taps. The Show Landmarks button toggles fingertip and hand pose visualization. This is optional for regular users, but it's helpful for alignment. The Recalibrate button restarts the geometry calibration process so that the user can realign the virtual keyboard to the desk. The Focus Editor button moves the cursor into the text area so that you can type immediately. It automatically toggles after calibration, and this Clear button empties the text area content.
To use the keyboard, the user first needs to calibrate it. When both index fingers are in the camera frame, an auto-calibration step runs and uses those 2 points to set the size, position, and rotation of the keyboard overlay. The left index finger corresponds to the F key and the right index finger corresponds to the J key. The keyboard overlay automatically freezes after 10 seconds. There is a recalibrate button to restart the process. After calibration, you can move your fingers without the overlay jumping around. The key label for where each finger is resting is rendered at the fingertip, so you can see in real time which key each finger is on. You can adjust the keyboard height and top to bottom ratio of the overlay. There is a reset to default button for each slider. Here's me typing with the vision-based tap detection. It misses a lot of my intended taps because we tuned it to avoid detecting taps that I didn't actually make. We minimized false positives here. And here's me typing with the pressure sensor tap detection. It sometimes detects taps I didn't make, but it almost never misses a real tap. It has significantly fewer false negatives than the vision-based tap detection.